Hello everyone. Today we are going to talk about the chapter 10, vapor and combined power cycle. So basically in chapter 9 we talked about the gas power cycle. So difference between the gas power and combined or vapor power cycle is the working fluid. So in gas power cycle we used single phase gas. However, in the vapor power cycle we are going to use the vapor that has two phase. Sometimes it will be vaporized, sometimes it will be condensed, right? And we also analyze the efficiency equation, how we can perform, or how we can increase the cycle efficiency. So objective of these vapor and combined power cycles are, the first objective would be that study of the working fluid that alternately vaporized and condensed, right? And then second objective would be that power generation, coupled with the process heating, which is called cogeneration. Basically in Brighton cycle we talked about the regeneration, right? How we can increase the efficiency or increase the cycle temperature. So in this chapter we will take a look at the cogeneration, how we can increase the efficiency, and how we can increase the cycle temperature. So number 3, it's basically we will talk about Rankine cycle, basic Rankine cycle. And then we'll talk about like how we can and modification, how we can modify to increase the cycle temperature and efficiency, right? Number 4 would be that basically that reheat and regenerative vapor cycle. So just like in the Brighton cycle we use the reheat, intercooling, and regenerator. So here we'll analyze those sort of stuff. Reheat, and lastly we will also talk about like how we can combine multiple cycle and analyze them, right? So combined cycles. All right. So before discussing, like before going to the Rankine cycle or the basic vapor power cycle, let's talk a look at some perspective of the vapor power cycle. Basically, that idealistic cycle. So the Carnot vapor cycle, it's kind of the ideal cycle. So basically, that Carnot vapor cycle is telling us that it's operate between two finite state and in a pure substance dome. So basically it's a TS diagram. In this diagram the Carnot cycle will look like this. So process 1 to 2, it's basically isothermal heat addition or heat transfer. Process 2 to 3, it's basically isentropic expansion through the turbine. And process 4 to 3 to 4, is condensation. And process 4 to 1, it's basically isentropic compression. Okay. So this is the ideal Carnot vapor cycle. Really, the limitation is, let's look at this. What are the limitation? So if we take a look at the process 1 to 2, which is the heat addition, this heat addition, they're saying that it should be isothermal. However, it is very difficult to achieve this process 1 to 2 in isothermal condition. Basically, adding the heat to the system. And also, if we want to increase the cycle temperature, we have to increase the temperature too, or we have to increase this temperature process, if we want to increase the efficiency. So that's the difficulties of this process. So this 1 2 process cannot be isothermal, or real life we cannot make this line isothermal. So somehow it needs to be, the temperature needs to be increased in this process. Another challenge is that isentropic expansion when 2 to 3. Basically here, the turbine cannot handle like moisturized or you know saturated vapor, because turbine blade will be deteriorated due to that, due to the impingement of those saturated vapor, right? So, and then another last challenge would be that isentropic compression, basically is a 4 to 1. So 4 to 1 is also a challenging process. It's because first of all, compressor cannot handle two phase working fluid that has like, compressor cannot handle like liquid working fluid, so it can handle the gas fluid. So that's a big challenge, right? So if I write the challenges or impracticalities, 1 to 2 process, it's basically difficult for isothermal. And then 2 to 3 process, it's basically turbine cannot handle moisture or slash saturated vapor, because it deteriorates the blade, right? And then 4 to 1, compressor cannot handle liquid vapor, right? So those are the difficulties or impracticalities of the ideal Carnot cycle. However, to minimize those ideal impracticalities, another Carnot cycle is proposed, or the modification of the Carnot cycle was brought into consideration, and that would be something like this. To increase the cycle temperature, the process 1 to 2, it's basically it's going in superheated region. However, still the impracticalities of this cycle, or this cycle is not realistic, because it's a isothermal condition, right? which is not which is very difficult to achieve in the boiler setup arrangement, or any kind of like the heat exchanger devices. However, another important thing is that another impracticalities still remain, is that this compression, isentropic compression, it's very hard, right? It is very difficult to generate or to obtain that high temperature, superheated and high temperature in the compressor. So it is very difficult, and also it is very difficult to achieve this isothermal process as well as the constant pressure process. So that's why the Carnot cycle, it's basically it cannot be an actual device. However, it's an ideal model, right, of the vapor power cycle. Based on that, people started to develop realistic model and try to see what are the limitations or how we can modify or how we can overcome those limitations, right? So the statement about this cycle, we can write that Carnot cycle is not a realistic cycle, rather it's a perspective, right? So there are some limitation. Knowing those limitation, let's go ahead and take a look in real life case, right? What are the things we need to consider in vapor power cycle? So one of the cycle or most prominently used cycle is that the Rankine cycle. So the Rankine cycle, basically, if you take a look, there are four basic components. Number one is pump replaced by compressor. Why? It's because a pump can handle the liquid or the vapor phase, right? However, compressor cannot handle that, so that's why we replace the compressor by pump. And also pump is a work consuming device, which you can see W pump incoming, right, to operate the pump. And then in the boiler, basically that high pressure liquid is coming to the boiler and getting vaporized, right, becoming vaporized. So this boiler operates like number of ways. It could be operates by nuclear reactor, right? So then we can call them nuclear power plant. It could be operated by like coal fired, right? um, Coal fired, basically, to generate the heat on the boiler or vaporize that steam. So yeah, coal fired. And then it could be solar, right? Concentrated solar power plant. Basically solar energy is used to generate the steam. And then whenever we have that steam, high pressure and high temperature steam, basically it's coming to the turbine and expanding, right? So when it's coming through the turbine, the temperature is dropping, and also volume is increasing, and pressure is also dropping in this turbine, right? So that turbine is producing the work, and we use that work to generate the electricity, basically to rotate a generator shaft, right? Generator shaft, and to produce electricity. However, we'll just analyze this cycle, okay? So from turbine, again, its turbine outlet is the still vapor, right? Saturated vapor. That vapor is coming through a condenser where the heat rejection is happening, and due to that heat rejection, that vapor is again it's becoming the saturated liquid. So if we divide this cycle, right, it has two sides. One side is liquid phase, right, and another side is vapor phase, right? So pure substance, it could be water, right? However, it has two different phases. So that's the difference between the Brayton cycle and vapor power cycle. Vapor power cycle has two phases, which is liquid and vapor. However, in the Brayton cycle, we saw that entire cycle operates in a single phase. Okay, so now let's take a look at what are the processes happening in this particular cycle. So if we write this cycle or process, let me draw the TS diagram first, and then we'll talk about those processes. So the TS diagram will look like this. So the first thing is the pump. It's slightly increasing the pressure, which is 1 to 2, and then in the boiler, right, it's becoming to the saturated line, and then here okay. So basically this is 3. You see that this is not anymore the isothermal process, right? So the temperature is maximizing, and this is number 4. A turbine outlet it's slightly it's coming to the moisture region or the saturated vapor region, right? So that's the TS diagram. Basically the Q in is happening here, and then Q out is right here, and then turbine work 3 to 4, W turbine, and then pump work 1 to 2, W pump. Okay, so now let's analyze this diagram. Okay, so the first thing is the process 1 to 2, which is the pump, right? And that pump it's basically working for isentropic compression. And then process 2 to 3, boiler. What is happening is isotherm constant pressure heat addition. Process 3 to 4, basically the turbine, and turbine is also isentropic expansion. And then process 4 to 1, it's basically the condensation, right? So it's basically the constant pressure heat rejection. Right, so now we know all of those processes, right? What is happening each of these processes. Now let's take a look at this energy analysis of this cycle. What would be the expression, right? So if we want to do the energy analysis, basically let's go for assumption. What are the assumptions we are making? So in this particular cycle, basically all of those component or all of those devices are steady flow devices. That means that constant amount of mass flow is incoming and constant amount of mass flow is outgoing. So similar to, like, boiler, turbine, condenser and pump, all of those devices has operating in a steady flow condition. So that's number one condition. So steady flow devices. Number two, it's basically no kinetic energy and potential energy of the working fluid, right? So those are the assumptions. So now if we do the energy analysis, then we'll see that what are the incoming energy. So basically that Q in minus Q out, right, plus W turbine minus W pump, it's nothing but it's changing the enthalpy of that working fluid, which is the enthalpy at the exit and enthalpy of the initial condition, right? So HI. Now we know that we know all of those thermodynamic property at all of this state. So for example, if we consider the pump, right, which is the process 1 to 2, the W pump or input equals to nothing but the H2 minus H1, right? So H1 is basically it's the enthalpy at state 1 and H2 is the enthalpy at state 2. So in chapter 7 we saw that if it is a steady flow device, right, constant amount of mass flow is coming and mass flow is outgoing, then the expression of the work would be something like this. Because we saw that dW equals to P D, excuse me, V dp, right? So that's what is we have to determine the pressure between two state, right? Where the P2 is greater than the P1 because the pump increases the pressure of the working fluid. Now let's take a look at the boiler. What is happening in the boiler, basically process 2 to 3. So the boiler, its heat addition is happening at constant pressure, which is we can write H3 minus H2, right? And then similarly in the turbine, the work is being produced Wt, which is H3 minus H4, right? And then in the condenser, heat rejection is happening Q out, which is equals to H4 minus H1. So now we know all of those thermodynamic properties at all of those state or all of those devices. We should be able to define the efficiency equation, right? So the thermal efficiency of this Rankine cycle is basically the net work output divided by Q in, or we can write it Q out divided by Q in. So that's the efficiency expression. However, in the United States, right, in the United States, people uses the efficiency expression in terms of the heat rate, right? So what is the heat rate? Heat rate is nothing but the amount of heat supplied to produce or generate basically 1 kilowatt hour of electricity. So that means that if we want to generate 1 kilowatt of hour of electricity, then how much heat we have to supply? That's the expression of the or that is the definition of the heat rate. So the efficiency equation in the United States basically used like something like this. So and one more important thing is that 1 kilowatt hour of electricity equals to 3412 BTU of energy. Okay, so basically it will be 3412 BTU per kilowatt hour divided by heat rate. So that's the efficiency expression. So just to give you an example, so if the heat rate is it's 11,363 kilowatt hour, then the cycle efficiency or the thermal efficiency of that particular cycle would be almost 30%. If you just plug in this value here, then you will get the efficiency is 30%. So now you can see that what is the significance or how the heat rate is being used for efficiency measurement. So that's all about this topic. Basically we talked about the ideal Rankine cycle and basic component about the Rankine cycle, and we also saw that energy balance equation, and we also saw the efficiency expression. So next class we will talk about the modification, and also we'll solve a math problem, so then we have better idea about the thermodynamic properties of each of the devices. So that's all for today, and thanks for watching this video. We'll come back with a new lecture. Thank you.